Hello there, and welcome to the channel. I'm so glad you found your way here tonight. Maybe you had a long day, one of those days where everything seemed to demand something from you. Maybe your mind is still spinning with all the little worries and tasks that never seem to stop. Or maybe you're simply the kind of person who likes falling asleep to deep thoughts and cosmic mysteries rather than counting sheep. Either way, tonight's journey is for you. You found a quiet place, and there's nothing more you need to do. Take a moment to settle in. Let your shoulders drop. Let your jaw relax. Let your breathing slow, becoming soft and steady, like waves on a distant shore. Let your body grow heavy against the mattress, as if gravity itself has loosened its grip just enough to let you sink into comfort. There's nowhere else you need to be, nothing else you need to think about. Because tonight, we're not simply stargazing. We're drifting into the darkest, strangest, most mysterious corners of the universe. We're going to talk about black holes. Black holes. The words alone carry a kind of weight, don't they? They conjure images of cosmic drains, of darkness absolute, of places where the rules we know cease to apply. They are regions where space curves in on itself, where time slows to a crawl and then seems to stop entirely, where even light, the fastest thing in the universe, cannot escape. They are the remnants of dead stars, the hearts of galaxies, and perhaps the most mysterious objects in all of existence. Scientists have spent over a century trying to understand them. Philosophers have pondered their implications, and still, they keep their secrets close, hidden behind horizons we can never cross. Tonight, we will explore 100 facts about these strange and wondrous objects. We will travel from the smallest black holes, no bigger than a city, to the largest, which contain the mass of billions upon billions of suns. We will talk about what happens when you fall into one, why time bends near their edges, and what they might tell us about the very nature of reality itself. Some of what you hear tonight may surprise you. Some may spark curiosity, little questions that linger at the edge of sleep. And some may simply drift past like clouds across the moon, half noticed, half forgotten, as you slip gently into dreams. And just before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. Now let your eyes grow heavy if they wish. Let your thoughts soften, and let's begin our journey into the dark. Now let's begin. Black holes are regions of space where gravity is so incredibly strong that nothing, not matter, not radiation, not even light itself, can escape once it ventures too close. This is the simplest definition of a black hole, but even these few words hint at something profound and strange. A black hole forms when a massive object collapses under its own weight, compressing all of its matter into an impossibly small point. The gravity near this point becomes so intense that it warps the very fabric of space and time beyond recognition. Light that wanders too close is bent inward, curved back upon itself, and swallowed into the darkness. Anything that crosses a certain invisible boundary, known as the event horizon, is lost to the outside universe forever. From the perspective of someone watching from far away, a falling object would appear to slow down and fade away, frozen at the edge of darkness for all eternity. But from the perspective of the object itself, it would cross into the black hole in an instant and continue falling toward the center. Black holes are not holes in the traditional sense, like a pit in the ground. They are objects, regions, places where the rules of physics twist into something deeply unfamiliar. They are among the most extreme environments anywhere in the cosmos, and they have fascinated scientists and dreamers alike for over 100 years. The idea of a black hole was first imagined over 200 years ago, long before Einstein was born, long before we had any real understanding of what light was or how gravity truly worked. In 1783, an English clergyman and natural philosopher named John Michell proposed the idea of what he called a dark star. He reasoned that if a star were massive enough, its gravity could be so strong that even light could not escape from its surface. Light, he believed, behaved like particles that could be affected by gravity and would be pulled back down to the surface of such a star like a ball thrown into the air. These dark stars would be invisible to distant observers, detectable only by their gravitational effects on nearby objects. Around the same time, the great French mathematician Pierre-Simon Laplace had remarkably similar ideas. Both men were working with Newtonian physics, which treats light as streams of particles influenced by gravitational attraction. Their calculations, though based on incomplete physics, were surprisingly close to what modern theory predicts. Of course, the true nature of black holes would not be understood until Albert Einstein's theory of general relativity transformed our understanding of gravity, space, and time over a century later. But the seed of the idea, the notion that gravity could become so powerful that it could trap light itself, was planted long ago by curious minds, simply staring up at the stars and wondering. Albert Einstein's general theory of relativity, published in 1915, provided the mathematical foundation that made black holes theoretically possible. In this revolutionary theory, gravity is not a force pulling objects together through empty space, as Newton had imagined. Instead, gravity is a curvature of space and time itself, caused by the presence of mass and energy. Massive objects like stars, planets, and galaxies bend the fabric of space-time around them, and other objects follow curved paths through this warped geometry. It is like placing a heavy ball on a stretched rubber sheet. The ball creates a dip, and smaller balls rolled nearby will curve toward it. The more massive the object, the deeper the dip, the greater the curvature. A black hole represents the most extreme case imaginable, a region where space-time curves so sharply that it folds in on itself, creating a one-way path inward. Einstein himself was deeply skeptical that such objects could actually exist in nature. He viewed them as mathematical curiosities, strange solutions to his elegant equations that seemed too extreme, too impossible to be real. But as the decades passed and astronomers gathered more and more evidence from distant stars and galaxies, it became undeniably clear that black holes were not just theoretical oddities. They were out there, scattered across the universe in their countless billions, shaping galaxies and swallowing stars. Einstein's equations had revealed something he himself never fully accepted. The universe was far stranger than even the greatest physicist of the age had dared to imagine. The term black hole was not coined until 1967, more than 50 years after Einstein published his theory of general relativity. The phrase was popularized by the American physicist John Archibald Wheeler, who used it during a lecture to describe these collapsed stellar remnants in a way that captured the public imagination before Wheeler's vivid and evocative language caught on. Scientists referred to these objects by far more cumbersome names: gravitationally collapsed objects, frozen stars, or simply Schwarzschild singularities, after the physicist who first calculated their properties. These terms were technically accurate, but utterly lacked poetry. Wheeler, a brilliant physicist and a gifted communicator, understood that science needed imagination as much as precision. The name black hole captured something essential about these mysterious objects: their absolute darkness, their deep strangeness, their sense of cosmic absence, the idea of a place in the universe where things could fall in but never come out. The term spread quickly through the scientific community and then out into the wider culture. It became one of the most evocative and memorable phrases in all of physics, appearing in countless books, films, and conversations. Wheeler himself was a towering figure in 20th century physics, a mentor to many of the era's greatest minds. But perhaps his most enduring and widespread contribution was not a formula or a proof. It was simply a name. Two short words that opened the door to wonder for millions of people around the world. There are several types of black holes, and they vary enormously in size, mass, and origin. The smallest and most common are called stellar black holes. These form when massive stars, those at least 20 or 30 times the mass of our sun, exhaust their nuclear fuel and collapse at the end of their lives. Throughout a star's life, that outward pressure from nuclear fusion in its core balances the inward pull of gravity. But when the fuel runs out, there is nothing left to support the star against its own weight. The core implodes in a fraction of a second, triggering a spectacular supernova explosion that can briefly outshine an entire galaxy. What remains at the center, if the original star was massive enough, is a black hole. Stellar black holes typically contain between 5 and several tens of times the mass of our sun. Yet all of that mass is compressed into a region only a few kilometers across, smaller than a city. These stellar black holes are scattered throughout the galaxy, often invisible and undetected unless they are actively consuming nearby matter. At the other end of the scale are supermassive black holes, which contain millions or even billions of solar masses. These giants sit at the centers of most large galaxies, including our own Milky Way. Between these two extremes are intermediate mass black holes, which range from hundreds to hundreds of thousands of solar masses. These are harder to detect and much less well understood, though recent observations have begun to reveal their presence. Each type of black hole tells a different story about the life and death of stars and the long, slow evolution of galaxies across cosmic time. The event horizon is the invisible boundary surrounding a black hole beyond which nothing can ever return. It is not a physical surface that you could touch or stand upon. There is no wall, no membrane, no barrier you could see or feel. It is simply the point of no return, the threshold where the escape velocity, the speed needed to break free of the black hole's gravity, exceeds the speed of light itself. Since nothing can travel faster than light, anything that crosses the event horizon is trapped forever, cut off from the outside universe for all eternity. From the perspective of a distant observer watching something fall toward a black hole, time appears to slow down as the object approaches the event horizon. Light from the falling object is stretched into longer and longer wavelengths, shifting from visible light to infrared to radio waves, growing dimmer and dimmer until it fades away entirely. The object seems to freeze at the edge, never quite crossing, an image that persists forever, though growing ever fainter. But from the perspective of the falling object itself, nothing unusual happens at the moment of crossing. There is no special sensation, no visible boundary, no sign that anything has changed. You would simply pass through, unaware that you had entered a region from which there is no escape, no signal, no message, no way to ever let the outside universe know what you found on the other side. The event horizon is invisible, intangible, and absolutely irreversible. At the very center of a black hole lies an object called the singularity, a point where all the mass of the black hole is thought to be concentrated. According to general relativity, the singularity has zero volume and infinite density, a place where the curvature of space-time becomes infinite and the known laws of physics completely break down. This is not a physical object in any ordinary sense that we can comprehend. It is a mathematical abstraction, a point where Einstein's equations produce meaningless answers, where dividing by zero gives infinity, where our theories confess their own limitations. Most physicists believe that the singularity represents the boundary of our current understanding, rather than a true physical feature of reality. A complete theory of quantum gravity, one that successfully unites the large-scale physics of general relativity with the small-scale physics of quantum mechanics, might finally reveal what actually happens at the heart of a black hole. Perhaps the singularity is replaced by something else entirely, a dense but finite core of exotic matter, a bridge to another region of space-time, a doorway to a baby universe, or something so strange that we cannot yet even imagine it. For now, the singularity remains one of the deepest and most profound mysteries in all of physics, a question mark lurking at the very heart of darkness. Black holes have only three properties that can be measured from the outside: mass, spin, and electric charge. This remarkable fact is sometimes called the no-hair theorem, a colorful phrase coined by John Wheeler to express the idea that black holes have no other distinguishing features, no hair, to tell them apart beyond these three basic numbers. No matter what fell into the black hole, whether it was a star, a planet, a cloud of hydrogen gas, a fleet of spaceships, or a library containing every book ever written, the end result is exactly the same. All that rich complexity, all that information, all those details are hidden forever behind the event horizon, completely inaccessible to the outside universe. The black hole is described entirely by just three numbers: how massive it is, how fast it is spinning, and how much electric charge it carries. In practice, most black holes are expected to have little or no electric charge, since any excess charge would quickly attract opposite charges from the surrounding environment and neutralize itself. So mass and spin are the two properties that truly define a black hole in the real universe. This extreme simplicity is mathematically elegant, but it is also deeply troubling from a physical standpoint. It suggests that enormous amounts of information, the complete description of everything that ever fell in, are somehow erased or hidden beyond recovery, raising profound questions about the nature of reality and the ultimate fate of information in the cosmos. If you were to fall into a stellar black hole, you would experience something known as spaghettification, one of the most vividly named phenomena in all of astrophysics. As you approached the singularity at the center, the gravitational pull on your feet, assuming you were falling feet first, would be significantly stronger than the pull on your head. This difference in gravitational force across the length of your body is called a tidal force, and near a small, stellar mass black hole, it becomes absolutely extreme. Your body would be stretched lengthwise by the stronger pull at your feet and compressed widthwise by the converging gravitational field, pulled into a long, thin strand of matter, like a piece of spaghetti being stretched thinner and thinner. The effect would be violent, catastrophic, and fatal, long before you ever reach the singularity itself. For larger black holes, however, the experience would be quite different. The tidal forces at the event horizon of a supermassive black hole are much weaker because the event horizon is so much farther from the central singularity. A person falling into a black hole with millions or billions of solar masses might actually cross the event horizon without feeling anything unusual at first, at least initially. But eventually, as they continued their inexorable fall toward the center, the tidal forces would grow stronger and stronger, and spaghettification would begin. It is a strange and gruesome fate. Yet one more reminder that the forces near a black hole are utterly unlike anything we experience in our everyday lives here on Earth. Time slows down near a black hole, and this is one of the strangest and most counterintuitive predictions of Einstein's general theory of relativity. It has been confirmed by numerous experiments here on Earth and in orbit around our planet. Gravity affects the passage of time. The stronger the gravitational field you are in, the slower time moves for you relative to someone in a weaker gravitational field. This effect, called gravitational time dilation, is incredibly small in everyday circumstances. Clocks at the top of a tall building tick slightly faster than clocks at the bottom, but the difference is only a few billionths of a second per day. Near the event horizon of a black hole, however, this effect becomes absolutely extreme. If you were to somehow hover just outside the event horizon of a black hole and then return to a distant spaceship, you would find that far more time had passed for your crewmates aboard the ship than had passed for you. You might have aged only minutes or hours while they aged years or decades. This effect is not an illusion or a trick of perception. It is a real, measurable, physical difference in the flow of time itself. Clocks near a black hole tick more slowly. Biological processes slow down. Every chemical reaction, every heartbeat, every thought is affected. The closer you get to the event horizon, the more dramatic the effect becomes, until at the event horizon itself, time, from the perspective of a distant observer, appears to stop entirely. Like an orbit a black hole, circling around it like a planet orbiting a star. At a certain distance from the center of the black hole, called the photon sphere, the gravitational pull is exactly right for light to travel in a circular path. Photons that enter this region at precisely the right angle will loop around the black hole, potentially multiple times, before either falling in or escaping outward into space. The photon sphere exists at 1.5 times the Schwarzschild radius, or 1.5 times the radius of the event horizon, for a non-rotating black hole. If you were somehow able to stand at the photon sphere and look straight ahead, you would theoretically see the back of your own head, because light could travel all the way around the black hole and return to your eyes. Of course, the photon sphere is not a stable or safe place to be. Any slight perturbation, any tiny push would send you either spiraling inward to your doom or flying outward into space. The orbits of photons there are unstable, balanced on a knife's edge. But the very existence of this strange region where light itself can orbit is a beautiful and profound example of just how dramatically black holes bend and warp the fabric of space-time in ways that completely defy our everyday intuition. Black holes can spin, and in fact, most black holes in the universe are rotating. When a massive star collapses to form a black hole, it carries its angular momentum, its spin, with it. Just as a spinning ice skater speeds up when they pull their arms in close to their body, the collapsing star spins faster and faster as it shrinks down to an ever smaller size. The resulting black hole inherits all of this rotation. A spinning black hole is described by a mathematical solution to Einstein's field equations called the Kerr metric, named after the New Zealand mathematician Roy Kerr, who discovered it in 1963, nearly 50 years after Schwarzschild's original non-rotating solution. Spinning black holes have some truly remarkable properties that set them apart from their non-rotating cousins. They drag the space-time around them, along with their rotation, an effect called frame dragging. Anything near a spinning black hole, even light itself, is pulled along in the direction of rotation. The faster the black hole spins, the more dramatic this effect becomes. There is also an outer boundary called the ergosphere, a region outside the event horizon where nothing can remain stationary no matter how hard it tries. Everything within the ergosphere must move in the direction of the black hole's spin. Spinning black holes are not merely theoretical curiosities. Observations strongly suggest that most black holes in the universe do indeed rotate, some at speeds approaching the maximum possible rate, nearly the speed of light at their equators. The fastest spinning black holes rotate at nearly the speed of light along their equators. There is a theoretical maximum spin rate for any black hole, determined by the delicate balance between the black hole's inward gravitational pull and the outward centrifugal forces generated by its rapid rotation. If a black hole were to spin any faster than this limit, strange things would happen. Its event horizon would shrink down to nothing, exposing the central singularity to the outside universe. This would violate a principle called cosmic censorship, a conjecture that holds that singularities must always be hidden, safely behind event horizons, never visible to outside observers. Observations of several black holes have revealed spin rates that approach this theoretical maximum limit remarkably closely. One black hole in the constellation Cygnus, known as Cygnus X1, one of the first black holes ever discovered, spins at more than 90% of the maximum possible rate. These extreme spin rates have profound effects on the surrounding space-time, on the behavior of the accretion disk, and on any matter or radiation falling toward the black hole. They also provide important clues about the black hole's history, since the spin rate can be increased or decreased over cosmic time by the accumulation of matter with different angular momentum. Despite what you might see in science fiction movies, Black holes do not suck things in like cosmic vacuum cleaners, relentlessly pulling everything toward them. This is one of the most common misconceptions about these objects. A black hole's gravitational pull at any given distance is exactly the same as that of any other object with the same mass. If our sun were somehow magically replaced by a black hole of equal mass right now, the Earth would not be sucked in. It would continue orbiting exactly as it does today, following the same path around the same center of mass. We would not be pulled to our doom. We would simply be left in cold darkness, orbiting an invisible point in space where the sun once shone. The key difference with black holes is that you can get much, much closer to the center of mass than you could with an ordinary star or planet. A star has a physical surface that stops you from falling any further inward. A black hole has no such surface. The event horizon is not a physical barrier, but simply the point of no return. As you get closer and closer to the center, the gravitational pull increases according to the same laws that govern all gravity. It is only when you venture too close, crossing that invisible threshold, that the trouble truly begins. But from a safe distance, a black hole is no more dangerous than any other massive object in the universe. The nearest known black hole to our solar system is approximately 1,560 light-years away. It is called Gaia BH1, and it was discovered in 2022 using data from the European Space Agency's Gaia Space Telescope, which has been precisely mapping the positions and motions of billions of stars throughout our galaxy. Gaia BH1 is a stellar black hole, roughly 10 times the mass of our sun, locked in an orbital dance with a sun-like companion star that completes one orbit every 186 days. Before this discovery, the closest known black hole was believed to be about 3,000 light-years away. There may well be even closer black holes that have not yet been detected, since isolated black holes that are not actively consuming matter are extraordinarily difficult to find against the dark backdrop of space. Gaia BH1 was identified by carefully observing the wobble of its companion star, a slight back and forth motion that revealed the gravitational presence of an unseen massive object. At 1,560 light-years, this black hole poses absolutely no threat to Earth. The distances involved are so unimaginably vast that we could never accidentally wander too close. But the discovery serves as a powerful reminder that black holes are scattered throughout our galaxy, hiding in the darkness between the stars, far more numerous than we once imagined. There may be hundreds of millions of black holes lurking in our galaxy alone. The vast majority of these would be stellar black holes, the dark remnants of massive stars that exploded as supernova long ago. Because black holes emit no light of their own, they are incredibly difficult to detect unless they happen to be actively interacting with nearby matter, pulling gas from a companion star, or drifting through a cloud of dust that lights up as it falls inward. An isolated black hole drifting silently through the interstellar void would be almost completely invisible, revealing its presence only through the subtle gravitational effects it might have on nearby stars or background light. Astronomers estimate the number of black holes in the Milky Way based on our best understanding of how many massive stars have formed and died over the roughly 13 billion year history of our galaxy. The estimates range from about 100 million to as many as 1 billion stellar black holes scattered throughout the galactic disk and the halo of old stars that surrounds it. In addition to these stellar remnants, there is the supermassive black hole at the very center of the Milky Way, and possibly a population of intermediate mass black holes hiding in the dense cores of ancient globular clusters. The universe is absolutely teeming with black holes, far, far more than we could ever hope to count or observe directly. The supermassive black hole at the center of our own Milky Way galaxy is called Sagittarius A, pronounced Sagittarius A star. It has a mass of approximately 4 million times that of our Sun, all of that enormous mass compressed into a region smaller than the orbit of Mercury around our own Sun. Sagittarius A is located roughly 26,000 light years from Earth in the direction of the constellation Sagittarius, which is best seen in the summer skies of the northern hemisphere. We cannot see the black hole directly with optical telescopes because it is hidden behind thick clouds of dust and gas that fill the center of our galaxy. But we can observe its effects on the stars that orbit nearby, some of which whip around the galactic center at tremendous speeds, completing their orbits in just a few decades or even less. By carefully tracking these stellar orbits over many years, astronomers have been able to calculate the mass and precise location of the black hole with remarkable accuracy. In May 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A, showing a glowing ring of superheated gas and dust surrounding a dark central shadow. It was the first time humanity had directly seen visual evidence of the black hole that sits at the very heart of our galactic home. The very first image of a black hole was released to the world in April 2019, and it immediately became one of the most iconic scientific images of our time. It showed the supermassive black hole at the center of the galaxy Messier 87, often called M87, a giant elliptical galaxy in the Virgo cluster. The image was captured by the Event Horizon Telescope, a remarkable global network of radio telescopes working together in perfect coordination as a single Earth-sized instrument. The black hole in M87 is vastly larger than Sagittarius A, with a mass of approximately 6.5 billion times that of our Sun, or more than 1,000 times the mass of our own galaxy's central black hole. Despite being 55 million light years away, an almost incomprehensible distance, its immense size made it an excellent target for imaging. The photograph reveals a bright ring of incandescent gas surrounding a dark central region, the shadow cast by the event horizon against the glowing background. The light comes from matter spiraling into the black hole at tremendous speeds, heated to temperatures of billions of degrees as it accelerates and compresses. The image confirmed many of the predictions of general relativity and marked the dawn of a new era in black hole astronomy. For the first time in human history, we could see with our own eyes the silhouette of one of the universe's most extreme and mysterious objects. The Event Horizon Telescope is not a single telescope, but a worldwide network of radio observatories scattered across the globe, from Hawaii to Chile, from Arizona to the South Pole. By carefully coordinating observations from all these different locations simultaneously, astronomers can create a virtual telescope with an effective diameter equal to that of the Earth itself. This technique is called Very Long Baseline Interferometry, and it allows for incredibly high resolution imaging that would be impossible with any single telescope alone. The data collected during the observations of the M87 black hole and later Sagittarius A amounted to petabytes upon petabytes of raw information so much data that it simply could not be transmitted over the internet in any reasonable amount of time. Instead, the data had to be physically shipped on hard drives to central processing facilities, where years of painstaking computational work were required to combine, calibrate, and analyze all the results. The achievement was a remarkable triumph of international scientific cooperation, bringing together more than 300 researchers from dozens of institutions around the world, all working toward the common goal of peering into the darkest corners of the universe. When matter falls toward a black hole, it often does not plunge straight in, but instead swirls around, forming a flattened, rotating structure called an accretion disk. As the material spirals slowly inward toward the event horizon, it heats up tremendously due to friction between particles moving at different speeds and the intense gravitational compression near the black hole. The inner regions of a typical accretion disk can reach temperatures of millions or even billions of degrees, far hotter than the core of any star, causing the disk to emit intense radiation across the entire electromagnetic spectrum, from radio waves to visible light to X-rays and gamma rays. Accretion disks around actively feeding black holes are among the brightest objects anywhere in the universe. The light pouring out from a black hole's accretion disk can outshine entire galaxies containing hundreds of billions of stars, even though the black hole itself, paradoxically, emits no light at all. This brilliant radiation is how astronomers first detected the presence of black holes decades ago. By observing the X-rays and other high-energy emissions streaming from these disks, scientists could infer the presence of extremely compact, extremely massive objects that could only be black holes. The accretion process is also remarkably efficient at converting mass into pure energy, far more efficient than nuclear fusion or any other process known to physics. A black hole consuming matter from an accretion disk can release up to 40% of the infalling material's mass energy as radiation, compared to less than 1% for the hydrogen fusion that powers stars like our sun. Some black holes launch incredibly powerful jets of matter and energy into space, beams of particles and radiation that can extend for thousands or even millions of light years across the cosmos. These jets shoot outward from the poles of the black hole, perpendicular to the plane of the accretion disk, traveling at velocities close to the speed of light. They are produced in the chaotic, energetic regions around rapidly spinning black holes with strong, twisted magnetic fields. Though the exact physical mechanism that creates and accelerates these jets is still not completely understood despite decades of study. The jets are composed primarily of charged particles, electrons and their antimatter counterparts called positrons, accelerated to tremendous velocities by the intense magnetic field lines that thread through the accretion disk and twist around as the black hole spins. As these jets plow through the thin gas that fills intergalactic space, they create enormous lobes of radio-emitting material that can grow to dwarf the galaxies they originated from. These jets play a surprisingly important role in the evolution of galaxies, injecting vast amounts of energy into the surrounding environment and influencing where and when new stars can form. They are among the most energetic and spectacular phenomena anywhere in the universe, visible across billions of light years, all powered ultimately by the rotation and gravitational pull of the black hole at their heart. Quasars are among the most luminous objects in the entire universe, and they are powered by supermassive black holes consuming matter at prodigious rates. The name quasar is short for quasi-stellar radio source because when these objects were first discovered in the early 1960s, they appeared as point-like sources of radio waves, looking very much like ordinary stars but emitting far more radio energy than any star possibly could. It was soon realized that quasars were incredibly distant, far beyond our own galaxy, and that their apparent brightness implied energy outputs greater than anything else known at the time, greater than entire galaxies full of stars. We now understand that quasars are the brilliant active nuclei of very distant galaxies, where a supermassive black hole at the galactic center is surrounded by a thick accretion disk of gas and dust falling inward. The light and radiation from the superheated accretion disk and the powerful jets can be seen across billions upon billions of light years, making quasars among the most distant objects we can observe in the universe. Because light takes time to travel, we see quasars as they existed billions of years ago in the young universe. Studying them helps astronomers piece together the story of how galaxies and their central black holes formed and evolved across the long history of the cosmos. The most distant quasars we have discovered are more than 13 billion light years away from Earth, which means their light has been traveling toward us for most of the entire 13.8 billion year age of the universe. When we look at these ancient beacons, we are seeing them as they were less than 1 billion years after the Big Bang itself, in an era when the universe was still young and the first stars and galaxies were just beginning to form. And yet, astonishingly, these early quasars already contain supermassive black holes with masses of billions of suns. How could such massive black holes have formed so quickly, so early in cosmic history? This is one of the greatest puzzles in modern astrophysics. In the standard picture, black holes grow gradually by consuming matter over time. But there simply does not seem to be enough time in the young universe for this slow process to create such enormous monsters. Some scientists have proposed that the very first black holes may have formed through a different mechanism, perhaps from the direct collapse of massive primordial gas clouds, bypassing the normal stellar phase entirely and creating black holes with tens of thousands of solar masses right from the start. Others suggest that conditions in the extremely dense early universe allowed for unusually rapid growth rates that are not possible today. The existence of these ancient, massive quasars challenges our understanding of black hole formation and forces us to reconsider the history of the very early cosmos. Black holes can collide and merge with each other, combining their masses into a single, even larger black hole. When two galaxies collide, a process that takes hundreds of millions of years to unfold, their central supermassive black holes are eventually drawn together by gravity and the friction of interacting with stars and gas. Over vast stretches of time, they spiral slowly inward, losing orbital energy through complex gravitational interactions with the surrounding matter. Finally, in the last moments of their spiral, when they are close enough for relativistic effects to dominate, they emit an intense burst of gravitational waves and merge into a single, larger black hole in a cataclysmic event that releases more energy than all the stars in the observable universe combined. Stellar mass black holes can also merge to typically in extremely dense stellar environments like globular clusters, where close encounters are common, or in binary systems where both stars collapse into black holes that eventually spiral together. These mergers release enormous amounts of energy, but not in the form of light or any kind of electromagnetic radiation. Instead, the energy radiates outward as gravitational waves, ripples in the very fabric of space-time itself. The detection of gravitational waves from merging black holes in 2015 opened an entirely new window onto the universe, allowing us to observe cosmic events that are completely invisible to traditional telescopes. Gravitational waves were first directly detected on September 14, 2015, by the LIGO Observatory in the United States, confirming a prediction that Albert Einstein had made exactly 1 century earlier in 1915. The signal came from 2 stellar black holes, each roughly 30 times the mass of our Sun, spiraling together and merging into a single black hole in a distant galaxy 1.3 billion light-years away. The gravitational waves traveled across that immense gulf of space until they finally reached Earth, stretching and squeezing the LIGO detectors by an almost unimaginably small amount, less than 1/10,000th the diameter of a single proton. This minuscule signal, lasting less than 1 second, represented the culmination of decades of technological development and represented an entirely new way of perceiving the universe. The discovery earned the 2017 Nobel Prize in Physics for the scientists who led the development of LIGO. Since that first historic detection, dozens of gravitational wave events have been recorded, including more black hole mergers, collisions between neutron stars, and even mixed mergers involving a black hole swallowing a neutron star. Each detection provides valuable new information about the population and distribution of black holes throughout the cosmos, and allows us to test our theories of gravity in the most extreme conditions imaginable. When 2 black holes finally merge together, they emit more energy in a fraction of a second than all the stars in the observable universe combined are radiating at that same moment. Most of this staggering release of energy comes out as gravitational waves during the final moments before the merger, when the 2 black holes are spiraling around each other hundreds of times per second at orbital speeds approaching the speed of light. The energy radiated can amount to several percent of the total combined mass of the 2 black holes, converted directly into ripples in space-time, according to Einstein's most famous equation, relating mass and energy. For a pair of stellar black holes with 30 solar masses each, this means that roughly 3 solar masses worth of energy, enough mass to build 3 entire stars like our Sun, is released as gravitational radiation in less than a second. Despite this absolutely enormous output of energy, gravitational waves interact so weakly with ordinary matter that they pass through everything, including the entire Earth, almost completely unnoticed. Detecting them requires instruments of extraordinary sensitivity, capable of measuring changes in distance far smaller than the diameter of a single atomic nucleus. Black holes do not last forever, though they come closer to immortality than almost anything else in the universe. In 1974, the legendary physicist Stephen Hawking made a revolutionary theoretical prediction that changed our understanding of these objects completely. Black holes emit radiation and slowly evaporate over time. This phenomenon, now universally known as Hawking radiation, arises from subtle quantum mechanical effects that occur near the event horizon. according to quantum mechanics, the vacuum of empty space is not truly empty, but is constantly fizzing with pairs of virtual particles that pop into existence and then annihilate each other almost instantaneously. Near the event horizon of a black hole, something remarkable can happen. One particle from such a pair can fall into the black hole, while the other escapes into space, carrying away a tiny amount of energy. Over incredibly long timescales, this slow drip of escaping particles causes the black hole to gradually lose mass and eventually evaporate away entirely. For stellar mass and supermassive black holes, this evaporation process is unimaginably slow, taking far longer than the current age of the universe. But for hypothetical very small black holes, if any exist, Hawking radiation could be significant and potentially detectable. The temperature of a black hole is inversely proportional to its mass, which means that larger black holes are colder, while smaller black holes are hotter. This counterintuitive relationship is a direct consequence of Hawking radiation. The typical energy of the particles emitted depends on the size of the event horizon, and smaller black holes have smaller event horizons and consequently higher temperatures. A stellar black hole with 10 times the mass of our sun would have a temperature of only about 6 billionths of a degree above absolute zero, unimaginably cold, far colder than even the faint cosmic microwave background radiation that fills all of space. Such a black hole would actually absorb more energy from the cosmic background than it emits as Hawking radiation, meaning it would slowly grow rather than shrink. But a hypothetical black hole with the mass of a large mountain would be much hotter, glowing with significant radiation, and a tiny black hole in its final moments of evaporation would heat up to absolutely enormous temperatures, releasing a burst of incredibly high-energy particles just before it winks out of existence forever. The time it would take for a typical stellar black hole to evaporate completely through Hawking radiation is so staggeringly long that it essentially defies human comprehension. A black hole with the mass of our sun would take approximately 10 to the power of 67 years to evaporate, a number so vast that writing it out in full would require a 1 followed by 67 zeros. The current age of the universe is only about 14 billion years, which is roughly 10 to the power of 10 years. Even the longest lived stars in the universe will have burned out completely, and all the galaxies will have scattered and faded into darkness long before the first stellar black holes begin to shrink in any measurable way. Supermassive black holes, those monsters at the centers of galaxies, will last even longer still, their evaporation times measured in 10 to the power of 100 years or more. These timescales extend into a future so impossibly remote that our current understanding of physics, and perhaps even the laws of nature themselves, may no longer apply. But eventually, if Stephen Hawking's remarkable prediction is correct, every single black hole in the universe will slowly fade away, leaving behind nothing but a faint whisper of radiation and the silent, empty void of space. Hawking radiation leads to one of the deepest unsolved puzzles in all of theoretical physics, known as the black hole information paradox. In quantum mechanics, one of the most fundamental principles is that information about the state of any physical system is never truly and permanently lost. Information may become scrambled, mixed up, extraordinarily difficult to access or decode, but in principle, it should always be possible to recover it if you know enough about the system's quantum state. When an object falls into a black hole, all information about what that object was, its composition, its history, everything that made it unique, seems to disappear forever behind the event horizon. If the black hole then evaporates completely over eons through Hawking radiation, what happens to all that information? Hawking's original calculations suggested that the radiation emitted by an evaporating black hole is perfectly thermal, completely random, carrying no information whatsoever about what originally fell into the black hole. This would mean that information is genuinely destroyed, violating a fundamental principle of quantum mechanics. Physicists have wrestled with this paradox for nearly 50 years now. Some believe that the information is somehow subtly encoded in delicate correlations within the Hawking radiation. Others suggest it is stored in some form on the event horizon itself, or escapes through some as yet unknown mechanism. The black hole information paradox remains one of the most profound and challenging unsolved problems in our quest to understand the fundamental nature of reality. Stephen Hawking himself was one of the most celebrated and beloved scientists of the 20th century, known worldwide for his groundbreaking work on black holes and cosmology, as well as for his remarkable personal story of triumph over adversity. Diagnosed with amyotrophic lateral sclerosis, a devastating motor neuron disease. At the age of just 21, he was initially given only a few years to live, yet he defied all expectations, living to the age of 76 and making profound contributions to our understanding of the universe that will endure for centuries. Hawking's prediction of black hole radiation, announced in 1974, was his most celebrated scientific achievement, brilliantly combining quantum mechanics with general relativity in a way that had never been done before. He also made fundamental contributions to our understanding of the Big Bang, the nature of time, and the tantalizing possibility of a unified theory of everything that would explain all the forces and particles in the universe. His popular science book, A Brief History of Time, introduced millions of readers around the world to the wonders and mysteries of the cosmos. Beyond his scientific work, Hawking became a beloved cultural icon, appearing on television shows, giving public lectures to packed audiences, and tirelessly advocating for science education and the wonder of discovery. His extraordinary life stands as an inspiring testament to the limitless power of the human mind to explore even the farthest and strangest reaches of the universe. Primordial black holes are a fascinating hypothetical type of black hole that may have formed not from dying stars, but in the extremely hot, dense conditions of the very early universe. Unlike stellar black holes, which require a massive star to collapse at the end of its life, primordial black holes could have formed from random density fluctuations in the incredibly hot plasma that filled the cosmos in the first fraction of a second after the Big Bang. In those earliest moments, the universe was so dense that if any region happened to have slightly more mass than average, it could have collapsed directly into a black hole before the universe had a chance to expand and dilute the concentration. Primordial black holes could theoretically come in an enormous range of masses, from less than a single gram all the way up to many times the mass of our sun. The smallest ones, if they ever existed, would have evaporated through Hawking radiation long ago. but larger primordial black holes could still be drifting through the universe today, invisible ghosts from the dawn of time. Some scientists have even proposed that primordial black holes might account for some or all of the mysterious dark matter, the invisible substance that makes up the vast majority of all mass in the universe, but has never been directly detected. The search for these ancient relics continues using gravitational wave detectors, gravitational microlensing surveys, and other increasingly sensitive techniques. A hypothetical black hole with the mass of an ordinary paperclip would be smaller than an individual atom and would evaporate in a tiny fraction of a second. Such a minuscule black hole would have an event horizon measured in billions of a meter, far smaller than any subatomic particle, smaller even than the distance scales at which quantum mechanical effects dominate. Its temperature would be unbelievably high, hotter than the core of any star, and it would radiate Hawking radiation at a furious, explosive rate, shrinking rapidly until it vanished in a brilliant flash of particles and high-energy radiation. Creating such a tiny black hole would require compressing the mass of that paperclip into an impossibly small space, concentrating matter to densities that are far, far beyond anything our current or foreseeable technology could achieve. Some physicists speculated a few decades ago that high-energy particle collisions in the most powerful accelerators, like the Large Hadron Collider, might be able to create microscopic black holes under certain exotic theoretical conditions. But extensive searches have found absolutely no evidence for this, and the energies involved in particle accelerators are many orders of magnitude too low under standard physics. If such tiny black holes were ever somehow created, they would pose no danger whatsoever, evaporating almost instantaneously before they could interact with anything else. Black holes serve as extraordinary natural laboratories for testing some of the most extreme and subtle predictions of Einstein's general theory of relativity. Near a black hole, gravity is so phenomenally strong that the effects predicted by Einstein's century-old theory become dramatically amplified and apparent. The bending of light around massive objects, the slowing of time in strong gravitational fields, the precession and shifting of orbital paths. All of these relativistic phenomena are magnified near a black hole to levels that can be precisely measured even across astronomical distances. Observations of stars orbiting Sagittarius A at the center of our galaxy have confirmed that their paths match the predictions of general relativity with remarkable, almost perfect accuracy. The images captured by the Event Horizon Telescope also agree beautifully with theoretical models of how light should bend and behave in the warped space-time near a black hole's event horizon. So far, Einstein's magnificent theory has passed every observational test we have devised. But scientists continue searching vigilantly for any tiny deviations that might hint at new physics beyond general relativity. Black holes are the ultimate proving grounds for our theories of gravity, natural experiments in regimes of extreme curvature and density that simply cannot be reproduced in any laboratory here on Earth. According to general relativity, once anything crosses the event horizon of a black hole, it has absolutely no choice but to continue falling toward the central singularity. This is not merely a statement that you would lack the rocket thrust or propulsion to escape. It is a much deeper and stranger statement about the very geometry of space-time itself. Inside the event horizon, all paths through space-time, even paths that intuitively seem to lead away from the center and back toward the outside universe, actually lead inexorably inward toward the singularity. In a sense that is difficult to visualize but mathematically precise, the roles of space and time become interchanged inside a black hole. The singularity is not best thought of as a place in space that you can avoid by steering around it. Rather, it is more like a moment in your future that you cannot escape no matter which direction you travel. Just as you cannot go backward in time in our everyday universe, you cannot avoid the singularity once you have crossed the event horizon. The geometry of space-time conspires against any escape. No matter how powerful your engines, no matter which direction you point them, you will reach the singularity. It is your inescapable future, the destination that awaits all who venture too close. The size of a black hole's event horizon is directly proportional to its mass. This crucial relationship is captured by a quantity called the Schwarzschild radius, named after the brilliant German physicist Karl Schwarzschild, who first calculated the properties of a non-rotating black hole in 1916, less than a year after Einstein published his general theory of relativity. The Schwarzschild radius is remarkably simple to calculate. It is approximately 3 kilometers for every solar mass. So a black hole containing 10 times the mass of our sun would have an event horizon roughly 30 kilometers in diameter, about the size of a small city. The supermassive black hole at the center of our Milky Way galaxy, Sagittarius A, with its 4 million solar masses, has a Schwarzschild radius of about 12 million kilometers. That sounds enormous, and it is, but it is still smaller than the orbit of Mercury around our sun. The truly monstrous black hole at the center of M87, with its 6.5 billion solar masses, has an event horizon roughly 40 billion kilometers across, larger than the entire orbit of Pluto, and then some. Despite their tremendous gravitational power and influence, black holes are remarkably compact objects when compared to the stars and galaxies they inhabit. Karl Schwarzschild derived his famous solution to Einstein's equations under the most extraordinary and difficult circumstances imaginable. In 1915 and 1916, he was serving as an artillery officer in the German army on the Eastern Front during World War I, enduring the brutal conditions and constant danger of trench warfare. Despite the chaos, suffering, and uncertainty all around him, he continued his scientific work by candlelight, sending his remarkable calculations by mail to Albert Einstein in Berlin. Schwarzschild's solution elegantly described the space-time geometry outside a perfectly spherical, non-rotating mass. And hidden within its mathematics was the prediction of what we now call the event horizon, the boundary from which nothing can escape. Tragically, Schwarzschild died just a few months after completing this work, not from the war directly, but from a rare autoimmune disease called pemphigus that he contracted while serving at the front. He never lived to see the full significance of what he had discovered. For decades afterward, his solution was viewed by most physicists as little more than a mathematical curiosity, an interesting but physically unrealistic consequence of Einstein's equations. It was only much later, as astronomers began observing the remnants of massive stars and probing the mysterious centers of distant galaxies, that the astonishing reality of black holes became undeniably clear. If you could somehow compress the entire Earth down to the density required to form a black hole, its event horizon would be less than 2 centimeters across, smaller than a marble. The Schwarzschild radius of any object depends only on its mass, and the Earth, despite its impressive size to us, is not particularly massive on cosmic scales. To create a black hole from our planet, you would need to squeeze all of the Earth's mass, all 6 trillion kilograms of rock, metal, water, and air, into a sphere smaller than a child's toy. No known natural process anywhere in the universe could accomplish such a feat, and the Earth will certainly never become a black hole through any natural means. But this thought experiment beautifully illustrates just how extreme the densities inside a real black hole must be. The matter that originally formed a stellar black hole, the core of a massive star that once spread across millions of kilometers, is compressed into a region just a few kilometers in diameter. And at the singularity itself, according to our current theories, the density becomes infinite. Black holes are places where ordinary matter is crushed utterly beyond recognition, where the very fabric of space and time is stretched and warped to limits we can barely imagine. The average density of a black hole, if calculated by dividing its total mass by the volume enclosed within the event horizon, actually depends surprisingly strongly on the black hole's size. And for the largest black holes, the result is counterintuitively low. This is because the volume of a sphere grows with the cube of its radius, while for a black hole, the radius of the event horizon grows only linearly with mass. For very large, supermassive black holes, the event horizon encloses such an enormous volume that the average density becomes quite modest by astronomical standards. A black hole with 1 billion solar masses would have an average density lower than that of ordinary water. An even larger black hole, one of the true monsters with tens of billions of solar masses, would have an average density lower than the air we breathe. Of course, this does not mean there is actually water or air distributed evenly inside these black holes. All the mass is concentrated at the central singularity, and the vast interior is filled not with matter, but with horrifically warped and twisted space-time. But the simple calculation reveals that supermassive black holes are not necessarily the densest objects in the universe, merely the most gravitationally extreme. Black holes profoundly challenge our understanding of what happens to matter at the most extreme densities and energies. At the singularity, according to the mathematics of general relativity, all the mass of the entire black hole is compressed into a single geometric point with 0 volume, and therefore infinite density. But most physicists strongly suspect that this cannot be the complete physical story. Infinite quantities appearing in a theory are usually warning signs that the theory has reached its limits, and something new and deeper is needed. Just as the infinities that plagued early 20th century quantum mechanics were resolved by the development of quantum electrodynamics, most researchers believe that a complete theory of quantum gravity will eventually resolve the singularity, replacing it with something finite, physical, and comprehensible. Leading candidates for such a theory include string theory, which posits that all particles are actually tiny vibrating strings, and loop quantum gravity, which proposes that space-time itself has a granular, discrete structure at the smallest scales. Some of these theoretical frameworks predict that the singularity is replaced by a region of extraordinarily high but finite density, Others suggest it might be a bridge or tunnel connecting to another region of space-time, perhaps even another universe entirely. Until a complete theory of quantum gravity is developed and tested, the true nature of what lies at the heart of a black hole will remain one of the deepest mysteries in all of physics. Wormholes are hypothetical tunnels or shortcuts through the fabric of space-time that might connect distant regions of the universe, or even different universes entirely. Some mathematical solutions to Einstein's field equations describe wormholes forming in connection with black holes. These are sometimes called Einstein-Rosen bridges, after Albert Einstein and his colleague Nathan Rosen, who first studied these strange geometric structures in the 1930s. The simplest Einstein-Rosen bridge connects two black holes, one in our universe and one potentially in another universe or another part of our own cosmos, with a tunnel or throat passing through a region that seems to exist outside normal space and time. However, these simple wormholes as originally described are highly unstable and would collapse far faster than anything, even light, could possibly travel through them. Later, theoretical work showed that a traversable wormhole, one that could actually be used as a shortcut, might be possible if held open by some exotic form of matter with negative energy density, a substance that has never been observed and may not exist in nature. The idea of using black holes or wormholes as portals to other places or times has captured the imagination of countless science fiction writers. But current physics offers little realistic hope that such journeys are practical or even possible. Some physicists have speculated even more boldly that black holes might actually be connected to entirely other regions of space-time, possibly even giving birth to new baby universes. This provocative idea arises from certain exotic solutions to Einstein's equations and from theoretical attempts to resolve the singularity problem by replacing the infinite density point with something else. If the singularity is not truly a point of infinite compression, but rather a transition or gateway to somewhere else, it might lead to a new, expanding region of space-time, a separate cosmos born from the gravitational collapse. In this picture, our own universe might have originated as the other end of a black hole in some parent universe, and every black hole in our cosmos might be spawning new universes of its own, forever beyond our ability to observe or contact. Other speculative models propose that black holes and their time-reversed counterparts, called white holes, might be connected. Matter and information falling into a black hole in one region might eventually emerge from a white hole somewhere else, perhaps in a distant part of our universe or in another universe altogether. These ideas remain highly speculative, far beyond what current observations can test or theory can firmly predict. But they illustrate the truly strange possibilities that emerge when we push our understanding of gravity and space-time to their ultimate limits. White holes are the theoretical, time-reversed counterparts of black holes, objects that are mathematically allowed by Einstein's equations, but may not actually exist in the physical universe. While a black hole is a region of space-time that nothing can ever escape from, a white hole would be exactly the opposite, a region that nothing can ever enter. Matter, energy, and light would stream outward from a white hole, expelled violently into the surrounding space. But nothing from outside could ever fall in, no matter how hard it tried. white holes emerge naturally from the mathematics of general relativity. If you take the equations describing a black hole and run them backward in time, you get a white hole. However, almost no physicists believe that white holes actually exist in nature. A white hole would require extremely special and improbable initial conditions that seem unlikely to have ever occurred in the real history of our universe. Furthermore, white holes appear to be unstable. The slightest perturbation would likely cause them to collapse into ordinary black holes. Some researchers have playfully speculated that the Big Bang itself, the explosive origin of our universe nearly 14 billion years ago, might have been a kind of cosmic white hole, an eruption of matter and energy from which we are still expanding outward. But for now, white holes remain fascinating theoretical curiosities, with no observational evidence to support their existence. One of the most mind-bending ideas in modern theoretical physics is the holographic principle, which suggests that all the information about what is inside a black hole might actually be encoded on its two-dimensional surface, the event horizon. This would mean that the three-dimensional interior of the black hole might be, in some deep sense, a projection or reconstruction of information stored on the two-dimensional boundary, much like a hologram encodes a three-dimensional image on a flat piece of film. The holographic principle was inspired by the groundbreaking work of Jacob Bekenstein and Stephen Hawking on black hole thermodynamics in the 1970s. They discovered that the entropy of a black hole, a measure of the disorder or information content of the system, is proportional to the area of its event horizon rather than its volume. This is deeply surprising. For ordinary objects, entropy scales with volume. The more stuff you have, the more ways it can be arranged, the more information required to describe it. But for black holes, the information capacity seems to depend only on the surface area. This strange result has led some of the boldest theoretical physicists to propose that perhaps our entire universe is holographic, that everything we experience in three-dimensional space might actually be encoded on a distant two-dimensional boundary at the edge of the cosmos. Black holes possess entropy, and in fact, they have more entropy than any other objects in the universe of comparable size. In physics, entropy is a measure of the number of different microscopic arrangements that could produce the same macroscopic state, essentially a measure of hidden information or disorder. In the early 1970s, the young physicist Jacob Bekenstein made the daring proposal that black holes should have entropy, challenging the prevailing view that they were perfectly simple objects with no internal complexity at all. Stephen Hawking's subsequent discovery of black hole radiation confirmed and extended Bekenstein's insight, demonstrating that black holes behave as thermodynamic systems with well-defined temperature, entropy, and energy, obeying laws analogous to the laws of thermodynamics that govern heat engines and refrigerators. The entropy of a black hole is absolutely enormous, proportional to the area of its event horizon measured in Planck units, the smallest meaningful length scale in physics. A stellar black hole with 10 times the mass of the Sun has more entropy than all the ordinary matter in the entire observable universe combined. This vast reservoir of hidden information is deeply puzzling because it is completely unclear where all that information is stored or what physical degrees of freedom it corresponds to. understanding black hole entropy is one of the central challenges in the quest for a complete theory of quantum gravity. The mathematical laws governing black holes bear a striking and profound resemblance to the laws of thermodynamics, the branch of physics that describes heat, energy, and the behavior of systems in thermal equilibrium. In classical thermodynamics, there are 4 fundamental laws describing relationships between temperature, energy, entropy, and equilibrium. Remarkably, in black hole physics, there are corresponding laws that describe relationships between surface gravity, mass, event horizon area, and other properties. The zeroth law of black hole mechanics states that the surface gravity of a stationary black hole is constant everywhere on the event horizon, just as the zeroth law of thermodynamics states that temperature is uniform throughout a system in equilibrium. The first law relates changes in a black hole's mass to changes in its horizon area, angular momentum, and charge, analogous to the first law of thermodynamics, relating changes in energy to heat and work. The second law states that the total area of all event horizons can never decrease, mirroring the statement that entropy never decreases in an isolated system. These deep parallels suggested long before Hawking radiation was discovered that black holes might not just be gravitational objects, but genuine thermodynamic systems with temperature and entropy arising from fundamental quantum properties that we are still struggling to fully understand. The area theorem, first proven by Stephen Hawking in 1971, states that the total surface area of all event horizons in the universe can never decrease over time. This remarkable result is often called the second law of black hole mechanics because of its close analogy to the second law of thermodynamics, which states that the total entropy of an isolated system can never decrease. When 2 black holes merge, the area of the resulting single black hole is always greater than or equal to the sum of the areas of the original 2 black holes. Energy can be extracted from a black hole in certain ways, such as by exploiting the rotation of a spinning black hole in a process called the Penrose mechanism. But this always results in a compensating increase in the event horizon area. The area theorem was dramatically confirmed by the LIGO and Virgo gravitational wave observations of black hole mergers, which showed that the area of the final black hole was indeed larger than the combined areas of the initial pair, exactly as the theorem predicted. However, Hawking radiation, which allows black holes to slowly shrink and evaporate over extremely long timescales, appears at first glance to violate the area theorem. Reconciling Hawking's quantum mechanical prediction with the classical area theorem and the second law of thermodynamics remains an active area of theoretical research. Supermassive black holes may play a crucial and perhaps even essential role in the formation and evolution of galaxies throughout the universe. Detailed observations over the past few decades have revealed that nearly every large galaxy has a supermassive black hole lurking at its center, and that the mass of this central black hole is remarkably well correlated with the properties of the surrounding galaxy, such as the total mass of stars in the central bulge, or the typical velocities at which those stars are moving. These tight correlations strongly suggest that the growth of supermassive black holes and the growth of their host galaxies are somehow intimately linked, that they have been influencing each other over billions of years of cosmic history. One important mechanism is called AGN feedback. When a supermassive black hole is actively accreting matter, the energy released by the infalling material can heat the surrounding gas, preventing it from cooling and collapsing to form new stars. This feedback process may regulate the growth of galaxies, determining their ultimate size and structure. Without supermassive black holes and the energy they inject into their surroundings, galaxies might look very different than they do today. Understanding this intricate dance between black holes and galaxies is one of the major goals of modern astrophysical research. The most massive black hole ever discovered contains approximately 6 billion times the mass of our Sun. This almost incomprehensible monster sits at the center of a distant quasar called TON 618, a blazingly bright point of light located about 10 billion light years away from Earth. The event horizon of this stupendous black hole is so large that our entire solar system, from the Sun all the way out past the orbit of Pluto and into the distant Kuiper Belt, could fit comfortably inside with plenty of room to spare. The diameter of the event horizon is roughly 130 times the distance from the Sun to Pluto. The existence of such enormous black holes raises profound questions about how they formed and how they managed to accumulate so much mass over the history of the universe. Even at the highest physically possible growth rates, it would take an extraordinarily long time to build up such a behemoth from an ordinary stellar mass seed. Some scientists have proposed that the very first supermassive black holes formed through unusual mechanisms in the early universe, perhaps from the direct gravitational collapse of massive primordial gas clouds that never went through the normal stellar phase. Others suggest that conditions in the young, dense universe allowed for exceptionally rapid accretion rates that are no longer possible today. Studying these most extreme examples of black holes helps us understand the limits of what is possible in our cosmos. And there, we pause for now, suspended at the edge of everything we have learned. We have traveled together from the first dreamlike imaginings of dark stars over 2 centuries ago to the largest black holes ever discovered, monsters containing the mass of billions of suns. We have explored event horizons and singularities, the paradoxes of information, and the slow whisper of Hawking radiation. We have witnessed gravitational waves rippling across the cosmos and marveled at the strange thermodynamics that govern these darkest of objects. 50 facts, each one a small window into an immense darkness, but our journey is only half complete. There is still so much more to discover, so many more mysteries waiting in the shadows between the stars, more questions about what lies inside a black hole, more wonders about their role in shaping the universe we see, more quiet revelations about the nature of space and time and reality itself. If you are still awake, the second part of our exploration awaits whenever you are ready. But if your eyes are heavy and your thoughts are drifting like clouds across a darkening sky, then stay exactly where you are. Let sleep take you the rest of the way. The black holes will still be there, patient and eternal, whenever you choose to return. Rest now, sleepy traveler. The universe will wait for you. It has been waiting for 14 billion years, and it will wait a little longer still. Let your breathing slow. Let your thoughts soften, and let the darkness carry you gently into dreams. So settle in once more. Find that comfortable position you were in before, or perhaps a new one that feels even better. Let your body relax completely into wherever you are resting tonight, whether that is a soft bed, a comfortable couch, or somewhere else entirely. Let your breathing become slow and steady, rising and falling like a gentle tide upon a peaceful shore. Let your thoughts soften at the edges, like watercolors bleeding into damp paper, the boundaries between ideas becoming gentle and blurred. We are going to continue our exploration of these cosmic mysteries, these extraordinary places where light cannot escape and time itself bends and stretches toward eternity. Some of what you hear may surprise you or spark a moment of quiet wonder. Some may simply drift past like stars through the window of a spaceship traveling through the night. And some may carry you gently, inevitably, sweetly into sleep. Let us continue our journey. Black holes can bend and magnify light from distant objects, acting as natural cosmic telescopes scattered throughout the universe. This remarkable phenomenon is called gravitational lensing, and it occurs because gravity warps the very fabric of space-time around any massive object. When light traveling from a distant galaxy or star passes through this warped region of space, it is bent from its original straight path, just as light passing through a curved glass lens is bent and refocused. If a black hole or any other massive object happens to lie along the line of sight between Earth and a more distant source, the black hole's gravity can bend the light around it in the beautiful and useful ways. Sometimes gravitational lensing creates multiple images of the same background object, each showing the source from a slightly different angle. Sometimes it stretches distant galaxies into graceful arcs and rings that curve around the lensing mass. And sometimes it simply brightens the distant source, focusing more light toward us than would otherwise reach our telescopes without the cosmic magnifying glass. In fortuitous cases, gravitational lensing can magnify the light from an extremely distant source by factors of 10, 50, or even more, allowing astronomers to see objects that would otherwise be far too faint to detect with any existing technology. This natural magnification has allowed us to study some of the most distant and ancient galaxies ever observed, peering back through billions of years of cosmic history to eras when the universe was young. The gravitational pull of a black hole can tear entire stars apart in catastrophic events called tidal disruption events. When an unlucky star wanders too close to a supermassive black hole at the center of a galaxy, the difference in gravitational force between the near side and the far side of the star becomes so extreme that the star is literally ripped to pieces, torn apart by these differential tidal forces before it can even cross the event horizon. Roughly half of the stellar material falls inward toward the black hole, forming a temporary accretion disk that heats up rapidly and glows brilliantly across the entire electromagnetic spectrum, from radio waves through visible light to X-rays. The rest of the disrupted star is flung outward into space in long, streaming tails of superheated gas that can stretch for light years through the galactic environment. These tidal disruption events produce distinctive flares of light that suddenly appear in the centers of otherwise quiet galaxies. Brightenings that astronomers monitoring the sky for transient phenomena can detect and study. They provide a unique and powerful way to study black holes that are otherwise completely dormant and invisible. Supermassive black holes that have been sleeping peacefully for millions of years, suddenly revealed when an unfortunate star ventures too close to their gravitational domain. astronomers have now observed dozens of these cosmic feeding events, each one a brief but brilliant window into the violent processes that occur near the event horizons of the largest black holes in the universe. Some supermassive black holes appear to be kicked completely out of their host galaxies, sent hurtling through the vast emptiness of intergalactic space at tremendous velocities with no possibility of ever returning home. These runaway or recoiling black holes are thought to form when two supermassive black holes merge together at the center of a galaxy, following a galactic collision. If the two merging black holes have different masses, different spin rates, or different spin orientations, the gravitational waves they emit during the final violent moments of their coalescence can carry away momentum asymmetrically, giving the newly merged black hole a powerful kick in one direction, much like the recoil of a cannon when it fires. Computer simulations of these mergers suggest that the recoil velocities can reach several thousand kilometers per second in extreme cases, fast enough to completely escape from even the largest and most massive galaxies in the universe. A few candidate recoiling black holes have been tentatively identified by astronomers studying galactic nuclei, including objects that appear to be offset from the centers of their host galaxies, or moving at unusual velocities relative to the surrounding stars and gas. If confirmed, these wandering giants would be among the most dramatic demonstrations of how gravitational waves can reshape the cosmic landscape. Ejected supermassive black holes would drift forever through the vast emptiness between galaxies, invisible and utterly alone, carrying with them whatever stars and gas happen to be bound closely enough to follow them into eternal exile. Binary black hole systems, in which two black holes orbit around their common center of mass, locked in a gravitational embrace, are surprisingly common throughout the universe. These gravitationally bound pairs can form through several different astrophysical pathways. Two massive stars that were born together in a binary star system can both collapse into black holes at the end of their lives, remaining gravitationally bound to each other across the gulf of space, just as they were when they were shining suns. Alternatively, two black holes that formed independently can be brought together through gravitational interactions in extremely dense stellar environments, such as the crowded cores of ancient globular star clusters or the chaotic centers of galactic nuclei, where millions of stars are packed into a relatively small volume. Once a binary black hole system forms, the two black holes begin a slow but inexorable dance, spiraling gradually toward each other over millions or even billions of years, losing orbital energy through the continuous emission of gravitational waves that ripple outward through the fabric of space-time at the speed of light. The final inspiral and merger happens relatively quickly once the black holes are close enough, lasting only seconds or fractions of seconds, and producing the powerful bursts of gravitational waves that observatories like LIGO and Virgo have now detected many dozens of times. Studying these binary black hole systems and their eventual mergers helps astronomers understand the complex processes of stellar evolution, the gravitational dynamics of dense stellar systems, and the fundamental physics of gravity operating in the strongest possible fields. The environment immediately surrounding an actively accreting black hole can host some of the most extreme magnetic fields anywhere in the universe. as matter spirals slowly inward through an accretion disk toward the event horizon. It carries magnetic field lines along with it, embedded in the ionized plasma like threads woven into fabric. The differential rotation of the disk, with inner regions orbiting faster than outer regions due to Kepler's laws of orbital motion, stretches and amplifies these embedded magnetic fields, winding them up tighter and tighter, like twisted rubber bands storing enormous amounts of energy. Near the inner edge of the accretion disk, perilously close to the event horizon, magnetic field strengths can reach values that are millions of times stronger than any magnetic field we have ever produced in laboratories here on Earth. These tremendously intense magnetic fields play crucial roles in the physics of black hole accretion. They help channel matter toward the black hole along specific paths. They contribute to the heating of the disk through magnetic reconnection events where field lines snap and release their stored energy. They are essential for launching the powerful relativistic jets that stream outward from some accreting black holes at nearly the speed of light, and they can extract rotational energy directly from spinning black holes through the remarkable Blandford-Znacek mechanism. Understanding the complex and turbulent behavior of magnetic fields in these extreme environments is absolutely essential for explaining the brilliant emissions we observe from quasars and active galactic nuclei scattered throughout the observable cosmos. Black holes can serve as the most powerful natural particle accelerators in the universe, boosting matter to energies far beyond what any machine built by human hands could ever achieve. The extreme gravitational fields and intense magnetic fields near a black hole can work together to accelerate charged particles, electrons, protons, and heavier atomic nuclei to velocities approaching arbitrarily close to the speed of light. These particles can then collide with other particles or with photons of light, producing cascading showers of high-energy radiation and secondary particles that stream outward into space. Some of the highest energy cosmic rays that reach Earth, individual subatomic particles carrying energies millions of times greater than those produced by the most powerful human-built particle accelerator. The Large Hadron Collider may well originate from the violent environments around supermassive black holes in distant active galaxies. The relativistic jets launched by accreting black holes are particularly effective particle accelerators, channeling streams of plasma outward at 99.9% of the speed of light and converting gravitational and magnetic energy into the kinetic energy of individual particles with remarkable efficiency. By studying the highest energy particles and radiation streaming from black hole systems across the universe, astronomers can probe physical conditions and processes that are utterly impossible to recreate in any laboratory on Earth. The concept of the no-hair theorem suggests that black holes are remarkably simple objects, fully characterized by just a handful of numbers, but recent theoretical work has revealed that this elegant simplicity may harbor subtle exceptions. The classical no-hair theorem states that a black hole, as seen from the outside universe, is completely and uniquely characterized by just three quantities: its total mass, its angular momentum or spin, and its net electric charge. All other information about what originally fell into the black hole is hidden forever behind the event horizon, inaccessible to outside observers for eternity. However, in recent years, physicists studying the quantum properties of black holes have discovered that black holes can carry additional soft hair, subtle quantum mechanical imprints on the event horizon that might encode some residual information about the black hole's past history. This soft hair is associated with certain symmetries of space-time that become important at the boundary of the event horizon and could potentially play a role in resolving the long-standing black hole information paradox. While these discoveries do not fundamentally overturn the basic picture of black holes as extremely simple objects from a classical gravitational perspective, they hint at a richer and more complex quantum mechanical structure, lurking at the mysterious boundary between what falls into the darkness and what forever remains outside in the light. The interior of a rapidly rotating black hole may contain truly bizarre mathematical structures called closed, time-like curves, paths through space-time that loop back upon themselves in time. According to the mathematics of the Kerr solution, which describes the space-time geometry around a spinning black hole, the region inside the inner horizon of a rotating black hole has such strange properties that it might be theoretically impossible to travel backward in time while remaining within that interior region. An observer following a closed, time-like curve would, after some journey through the twisted space-time, return to the exact moment from which they departed, creating all the paradoxes that time travel stories love to explore. However, most physicists believe that these exotic closed, time-like curves are artifacts of the idealized mathematical solution and would not survive in any real black hole formed from actual physical matter. The inner regions of a rotating black hole are expected to be highly unstable, with any perturbation causing the smooth mathematical geometry to break down into something far more chaotic. Still, the existence of these solutions within Einstein's equations reminds us just how strange the interior of a black hole might truly be. Black holes may provide crucial clues about the ultimate fate of the universe in the incomprehensibly distant future. In the far future, long after all the stars have exhausted their nuclear fuel and burned out, long after the galaxies have scattered and faded, black holes will be among the last remaining concentrations of organized matter and energy anywhere in the cosmos. Stellar black holes will drift through the cooling universe, occasionally encountering and consuming stray particles. Supermassive black holes will persist even longer, slowly evaporating through Hawking radiation over timescales beyond imagination. Eventually, even the most massive black holes will fade away, their final evaporation releasing a last whisper of radiation. After the last black hole evaporates, the universe may enter an eternal era of near total emptiness. Black holes, the most extreme objects in the current cosmos, will be the last lights to go out, the final chapter before the eternal dark. The shadow of a black hole, the dark silhouette seen against a bright background, has a shape that depends on the black hole's spin rate and our viewing angle. For a non-rotating Schwarzschild black hole, the shadow is a perfect circle. For a rapidly spinning Kerr black hole, the shadow becomes asymmetric, compressed on one side by frame dragging. By measuring the precise shape of a black hole's shadow, astronomers can determine how fast it is spinning, testing general relativity in the strongest fields. The images from the event horizon telescope show shadows consistent with Einstein's predictions, though future observations will provide more detailed measurements. Some physicists propose that black holes might not contain singularities at all, but instead harbor dense cores of exotic matter. General relativity predicts infinite density at the center, but this may break down when quantum effects become important. Various proposals have been made for what might replace the singularity: quantum pressure halting the collapse, exotic phases of matter, or quantum bounces, creating new regions of spacetime. These alternatives remain speculative, but are motivated by the expectation that quantum gravity will resolve the unphysical infinities of a classical theory. The cosmic censorship conjecture holds that singularities must always be hidden behind event horizons, never visible to the outside universe. Proposed by Roger Penrose in 1969, this principle suggests that nature prevents naked singularities from affecting the predictability of physics. The conjecture has never been proven in full generality, though most physicists believe it holds in realistic situations, ensuring that the breakdown of physical laws at singularities remains safely quarantined behind event horizons. Roger Penrose shared the 2020 Nobel Prize in Physics for proving that black hole formation is a robust prediction of general relativity. His 1965 singularity theorem showed that once gravitational collapse begins under general conditions, singularity formation is inevitable. This demonstrated that black holes are generic outcomes of stellar death, not exotic special cases. Penrose shared the prize with Andrea Ghez and Reinhard Genzel, who received it for their observations of the supermassive black hole at the center of our Milky Way galaxy. Black holes emit no light themselves, yet they can power the most luminous objects in the universe. The light comes from matter in the accretion disk, heated to billions of degrees as it spirals inward. The most luminous quasars outshine entire galaxies containing hundreds of billions of stars. Their light has traveled billions of years to reach us, carrying information about the young universe. Black holes, despite their fundamental darkness, serve as some of the most powerful beacons in creation. The first stellar black hole ever discovered was Cygnus X1, identified in 1971 as one of the strongest X-ray sources in the sky. Located about 6,000 light-years away, it is a binary system where a black hole pulls material from a massive companion star. The discovery provided the first strong evidence that black holes exist in nature. Stephen Hawking famously bet against it being a black hole, conceding in 1990. Recent measurements show the black hole has about 21 solar masses and spins at nearly maximum rate. Black hole X-ray binaries cycle through different states of activity, alternating between quiet periods and dramatic outbursts. During quiescence, accretion is slow and radiation minimal. During outbursts, the luminosity can increase by factors of thousands. These transitions involve changes in accretion, disk structure, and jet properties. Studying them helps astronomers understand accretion physics and the disk-jet connection. X-ray binaries serve as laboratories for studying matter in extreme gravitational fields. Microquasars are stellar mass black holes in our galaxy that mimic the behavior of distant quasars on smaller scales. They have accretion disks and relativistic jets like their supermassive cousins. Because they are nearby, changes that would take millennia in quasars can be observed over days in microquasars. Some display apparent superluminal motion, an optical illusion when jets point toward us. Studying microquasars has provided key insights into the physics of accretion across all mass scales. Black hole spin can be measured through several techniques. X-ray spectroscopy reveals how close the inner accretion disk extends to the horizon. which depends on spin. Quasi-periodic oscillations in X-ray light curves may relate to inner disk frequencies. Gravitational wave observations encode spin information in the waveform. These methods have revealed a wide range of spin rates, from nearly zero to nearly maximum. Each measurement technique has its own strengths and systematic uncertainties. The energy extractable from a spinning black hole is enormous, up to 29% of its total mass energy for maximum spin. This far exceeds nuclear fusion efficiency. The Penrose process allows particles to extract rotational energy in the ergosphere. The Blandford-Znacek mechanism extracts energy via magnetic fields, powering relativistic jets. These processes gradually spin down the black hole over millions of years, while transferring its rotational energy to the surrounding environment. Black holes may be responsible for gamma-ray bursts, the most energetic explosions in the universe. Long-duration bursts are associated with massive star deaths, where the core forms a black hole. Material falling back creates jets moving at 99.9% of light speed. When these jets point toward Earth, we see brilliant gamma-ray flashes. Short-duration bursts arise from neutron star mergers, confirmed by the coincident detection of gravitational waves and a short burst in 2017. When a neutron star merges with a black hole, the outcome depends on their masses and spins. If the black hole is much larger, it may swallow the neutron star whole without disruption. If smaller or rapidly spinning, tidal forces can tear the neutron star apart, creating a brief accretion disk and possibly a gamma-ray burst or kilonova. These events produce gravitational waves encoding information about both objects. The first confident detections came in January 2020, opening a new observational window. The boundary between black holes and neutron stars involves a maximum mass for neutron stars, above which they must collapse. This limit lies between about 2 and 3 solar masses, depending on the uncertain equation of state of ultra-dense matter. Gravitational wave observations are helping constrain this limit. Discovering compact objects in the mass gap between neutron stars and black holes would have profound implications for our understanding of stellar evolution and extreme matter physics. There appears to be a gap in black hole masses between about 55 and 120 solar masses due to pair instability supernovae. In very massive stars, gamma rays convert to electron-positron pairs, removing pressure support and triggering a runaway explosion that completely destroys the star. This prevents black hole formation in that mass range. Above 120 solar masses, the implosion is too rapid for the explosion to unbind the star. Finding a black hole in this gap would suggest mergers of smaller black holes or incomplete stellar evolution theory. Gravitational wave detections have revealed unexpectedly heavy stellar black holes, with many having masses of 20 to 40 solar masses. These may have formed from low metallicity stars that lose less mass through stellar winds. Alternatively, some may have grown through previous mergers. The population of merging black holes also reveals information about their formation environments, whether in galactic fields or dense stellar clusters where gravitational encounters can bring black holes together. Black holes can form through exotic processes beyond ordinary stellar collapse. Direct collapse black holes might form from massive gas clouds in the early universe, creating seeds of tens of thousands of solar masses. Runaway stellar collisions in dense clusters might build up massive objects that collapse. Very massive stars above 250 solar masses might collapse directly without supernovae. As observations improve, we may discover black holes formed through pathways not yet imagined, how supermassive black holes grew so large so quickly remains one of the biggest unsolved problems in astrophysics. The most distant quasars already contain billion solar mass black holes less than 1 billion years after the Big Bang. Growing so large through ordinary accretion would require continuous feeding at maximum rates. Some propose heavy initial seeds from direct collapse. Others suggest in periods of super Eddington accretion. Understanding the first supermassive black holes is closely connected to understanding the first galaxies. Black holes at galactic centers cycle between activity and dormancy. During active phases, the nucleus can outshine all the galaxy's stars as a quasar. During quiet phases, the black hole is nearly invisible. Our own Sagittarius A is currently dormant, accreting very little. Evidence suggests it was more active in the past, perhaps responsible for the giant gamma-ray bubbles extending above and below the galactic plane. Over cosmic time, supermassive black holes alternate between feeding and fasting. The gravitational influence of supermassive black holes can affect entire galaxies through feedback processes. Energy from jets and winds can heat gas, blow it out of galaxies, or prevent star formation. This may explain correlations between black hole mass and galaxy properties. Without black hole feedback, simulations produce overly massive galaxies. Black holes act as thermostats, regulating star formation and shaping galactic structure over billions of years. Some galaxies contain binary supermassive black holes at their centers, the result of galaxy mergers. The two black holes sink toward the center through dynamical friction, eventually spiraling together through gravitational wave emission. Several candidates have been identified with separations of just a few light years. Their final coalescence would produce gravitational waves detectable by future space-based observatories. Binary supermassive black holes help us understand black hole growth through mergers. Triple supermassive black hole systems may exist when a galaxy with a binary merges with a third galaxy. The dynamics of three massive objects can be chaotic, potentially ejecting one black hole through a gravitational slingshot. Triple interactions can also accelerate the merger of the remaining pair. A few candidate systems have been reported based on observations of multiple active nuclei. These exotic configurations provide laboratories for studying complex gravitational dynamics. The smallest supermassive black holes, with masses of only a few 100,000 suns, may provide clues about how the first black holes formed. Found in dwarf galaxies that have not experienced many mergers, they may preserve conditions similar to the early universe. If supermassive black holes grew from small seeds, we would expect intermediate mass black holes in dwarfs today. Surveys are gradually revealing the demographics of these smallest supermassive black holes. Intermediate mass black holes, between 100 and 100,000 solar masses, occupy a mysterious middle ground. They may form from runaway stellar collisions in dense clusters, mergers of smaller black holes, or direct collapse of very massive stars. Ultraluminous X-ray sources may be powered by intermediate mass black holes. The 2019 gravitational wave detection GW190521 revealed a black hole of about 142 solar masses, firmly in the intermediate mass range. Pulsars orbiting black holes would be extraordinary laboratories for testing general relativity. Pulsars emit precisely timed radio pulses that would be delayed and advanced by orbital motion around a black hole. By monitoring these timing variations, astronomers could measure black hole properties with unprecedented precision. Despite extensive searches, no pulsar black hole binary has been definitively identified, but the discovery remains a holy grail of pulsar astronomy. The environment near a black hole would be instantly lethal to any unprotected spacecraft or human. X-rays and gamma rays stream from the accretion disk. Charged particles and jets carry enough energy to destroy anything in their path. Even at considerable distances, the radiation environment would be hostile. Science fiction portrays black holes as destinations, but the reality is far less hospitable. Black holes are fascinating to study from afar, but deadly to approach. Some have speculated about advanced civilizations harnessing black holes as energy sources. The Blandford's Najek mechanism could provide essentially unlimited power. Dyson sphere-like structures might capture radiation from accretion. These ideas remain speculation, but they illustrate the extraordinary energy resources black holes represent. If advanced life exists elsewhere and has developed far superior technology, black holes might be among the resources they exploit. Black holes have become important tools in the search for dark matter. Primordial black holes themselves could be the dark matter. Dark matter particles near black holes might annihilate and produce detectable radiation. Stellar motions around supermassive black holes constrain dark matter distributions in galactic centers. Gravitational wave observations probe whether dark matter halos influenced black hole mergers. As observations improve, black holes may help solve one of physics' biggest mysteries. The cosmic web of galaxies and dark matter may channel gas toward supermassive black holes. Galaxies are arranged in filaments, sheets, and nodes with voids in between. Gas flowing along filaments funnels into galaxies, providing fuel for black hole growth. The most massive galaxies at cosmic web nodes may have particularly well-fed black holes. Understanding how the cosmic web connects to black hole activity links the largest structures in the universe to some of its smallest and densest objects. Black hole physics has inspired new approaches to quantum computing and information theory. The black hole information paradox has led to insights about the nature of information itself. Some researchers draw analogies between black holes and quantum error-correcting codes. The holographic principle suggests information content depends on surface area, not volume. These ideas have found applications beyond astrophysics and may lead to practical advances in quantum computing. The firewall paradox has sharpened debates about what happens at the event horizon. Traditional physics suggests falling observers notice nothing special at the horizon. But quantum entanglement arguments suggest a wall of high-energy particles might surround the horizon. Different resolutions have been proposed. The interior might not exist as imagined, or entanglement structure might be modified near the horizon. The firewall debate highlights how poorly we understand the quantum nature of black holes. Black holes might create quantum entanglement between distant particles. Some proposals suggest black hole interiors could be connected through wormholes related to quantum entanglement. The slogan, ER equals EPR, connects space-time geometry with quantum correlations. If correct, space-time itself might emerge from patterns of entanglement. These ideas are speculative but represent ambitious attempts to understand quantum gravity and the fundamental structure of reality. The next generation of gravitational wave detectors will open new windows onto the black hole universe. The Einstein telescope and Cosmic Explorer will be ground-based detectors with far greater sensitivity. The space-based LISA mission will detect mergers of supermassive black holes across the universe. Pulsar timing arrays are already constraining gravitational waves at even lower frequencies. Together, these observatories will reveal the full gravitational wave spectrum. Extreme mass ratio spirals, where stellar objects spiral into supermassive black holes, will be key targets for LISA. As the smaller object orbits thousands of times, gravitational waves encode detailed information about space-time geometry. These signals will map supermassive black hole spacetimes with exquisite precision, testing whether they match general relativity. They are also sensitive to surrounding matter and dark matter. Halos, extreme mass ratio spirals promise powerful probes of black hole physics. The Event Horizon Telescope collaboration plans to create movies of gas orbiting black holes. The first images were single snapshots, but matter orbits the event horizon in hours or days. Future observations will capture sequences showing this orbital motion, creating movies of material swirling around black holes. Watching gas orbit and fall in will provide unprecedented insights into accretion physics, jet launching, and the behavior of light in the strongest gravitational fields. Black holes might be surrounded by exotic structures called gravitational atoms if ultralight bosonic particles exist. Particles like axions could accumulate around spinning black holes through superradiance, forming cloud-like structures bound by gravity. The cloud would grow by extracting rotational energy until equilibrium is reached. Such clouds could be detected through gravitational effects or signatures in merger waveforms. Searching for gravitational atoms provides a novel way to hunt for new particles beyond the standard model. The study of black holes has driven major advances in theoretical physics over the past century. Attempts to understand singularities have motivated quantum gravity research. The information paradox has led to new insights about entropy and space-time structure. The holographic principle has transformed our understanding of gravity and quantum field theory. String theory has made black holes central to its program. Black holes sit at the intersection of gravity, quantum mechanics, and thermodynamics, making them uniquely powerful tools for probing the deepest questions. Black holes have captured human imagination like few other scientific concepts, appearing throughout literature, film, and popular culture. From science fiction to Interstellar's stunning visualizations, black holes have become icons of cosmic wonder and existential mystery. They represent the ultimate unknown, places where familiar rules break down. The first black hole image became an instant cultural phenomenon. Black holes resonate with deep human themes: the fear of annihilation, fascination with the infinite, and longing to understand what lies beyond knowledge's edge. The study of black holes reminds us how much we still do not know about the universe. Despite over a century of work, fundamental questions remain unanswered. What happens at the singularity? How is information preserved? What formed the first supermassive black holes? How does quantum mechanics change our picture? Each answer generates new questions. Black holes, at the intersection of the very large and very small, are perhaps the ultimate frontier, challenging us to develop new theories and new ways of thinking about the cosmos. Black holes will still exist long after the last stars have burned out. In the far future, after star formation ceases, stellar black holes will persist for 10 to the power of 67 years. Supermassive black holes will endure even longer. These dark remnants will be the last organized structures before final evaporation. The age of black holes will be the last great epoch before eternal darkness descends upon the cosmos. Perhaps the most profound lesson black holes teach us is about the limits of our understanding. They are objects where general relativity and quantum mechanics come into direct conflict. They contain regions where theories give infinite or meaningless answers. They pose paradoxes that have resisted resolution for decades. And yet we have learned so much. We can observe their shadows, hear their mergers, and map their influence. The study of black holes is a testament to human curiosity and determination to understand even the most alien corners of nature. And so we arrive at our 100th and final fact. Black holes, for all their strangeness, are part of the natural universe. They obey physical laws, even when those laws take unfamiliar forms. They are born from stellar deaths, grow through matter consumption, and eventually fade through Hawking radiation. They are not supernatural portals or magical gateways, but genuine astrophysical objects that emerge inevitably from the physics of gravity and space-time. Understanding them scientifically does not diminish their wonder, but deepens it. They show us that the universe is stranger and more beautiful than ordinary experience suggests. That reality extends far beyond our senses. Black holes are invitations to imagine, to calculate, to observe, to wonder. They are reminders that the universe still holds mysteries worthy of a lifetime of contemplation. And that is perhaps the most wonderful thing of all. And so our journey comes to its end. 100 facts about black holes, 100 windows into the deepest darkness the universe offers. We have traveled together from the earliest imaginings of dark stars in 18th century minds to the gravitational wave observatories of today. We have explored event horizons and singularities, Hawking radiation and information paradoxes, quasars blazing across billions of light years and quiet black holes sleeping at galactic hearts. We have contemplated the births and deaths of stars, the slow growth of galaxies, and the ultimate far future fate of the cosmos itself. I hope this journey has given you something beautiful to dream about tonight. Perhaps you will drift off thinking of swirling accretion disks or the gentle evaporation of ancient black holes over timescales beyond imagination. Perhaps you will wonder about the singularity, where all our knowledge gives way to beautiful uncertainty. Or perhaps these words have already faded into the soft edges of approaching sleep, half-remembered fragments coloring your dreams in shades of cosmic darkness and a distant starlight. However you have arrived at this moment, I am deeply glad you are here. The universe is vast beyond measure, strange beyond expectation, and full of wonders we are only beginning to glimpse. Black holes are among the strangest places where space-time folds in on itself, where time slows toward eternity and light bends toward annihilation. They remind us that there is always more to discover, always deeper mysteries waiting beyond the edge of what we know. So rest now, gentle traveler. Let your breathing slow to a peaceful rhythm. Let your thoughts drift like stars through the endless night. The black holes will still be there when you wake, patient and eternal, holding their secrets close until you are ready to wonder about them again. Thank you for listening. Thank you for dreaming. And thank you for traveling through the universe with me. Good night, sleepy traveler. May your dreams be filled with stars.